Ever wondered how far a Maxwell aircraft can truly fly? We decided to find out. The Maxwell aircraft has already turned heads across the aviation world. With its radical design and electric propulsion, it represents a leap forward in flight technology. Its sleek lines and whisper-quiet operation mark it as something different, something special. What people really want to know, though, is just how far this marvel can go. What is its real endurance in the skies? Can it handle ultra-long-range missions with the kind of reliability needed for modern travel? We set out to answer these questions once and for all. Our journey began with a single, bold objective to push the Maxwell aircraft to its absolute limit. We weren't just flying for speed or altitude, we were flying for distance. This was a test of persistence, engineering, and sheer willpower. Before we even reached the cockpit, months of preparation had gone into this moment. The Maxwell is no ordinary aircraft, and this was no ordinary mission. We assembled a team of experts in aviation, data analysis, and safety management. From the very beginning, every detail had to be perfect. We started by analyzing the aircraft's baseline performance on past missions. We looked at battery efficiency, thermal limits, and in-flight power draw. Then we moved into simulation. Advanced modeling software helped us test various scenarios without ever leaving the ground. Every single flight path was carefully considered. Weather models were integrated, backup routes were mapped, emergency contingencies were drawn up in full detail. Once the data supported our theoretical limits, we began planning for real-world execution. Choosing the right location was crucial. We needed an airfield with minimal traffic, favorable weather, and excellent support infrastructure. After reviewing several candidates, we selected a remote but fully equipped site in Namibia. The climate offered stable air conditions and the local team was ready to assist. Next came the physical preparation of the aircraft itself. Technicians inspected every component from wing bolts to battery packs. Software was updated to the latest build, including flight control systems and telemetry protocols. Then came weight optimization. To maximize range, unnecessary items were removed, and the cabin was streamlined. Sensors were installed at critical points to monitor stress, temperature, and battery degradation. 2 pilots were selected for the journey, each with over 3,000 hours of flight experience. They underwent psychological and physical testing to ensure readiness for a prolonged mission. Nutritionists crafted special meal plans to maintain focus and stamina. Custom in-flight hydration systems were installed within the cockpit. All of this led us to one day, the day of departure. As dawn broke, the Maxwell aircraft stood gleaming on the runway. It had never looked more alive. A quiet hum indicated systems were online. Ground crews made final checks. A light breeze ruffled the surface of the runway. Inside the control tower, engineers and observers stood tense but hopeful. At exactly 0600 hours, clearance was given. The aircraft rolled forward smoothly. Acceleration was swift but silent. At 0700 feet, the aircraft leveled off, banking gently into its predetermined flight path. The flight had begun. Initial performance metrics were stable. Power consumption was within acceptable limits. The aircraft was behaving as expected. Altitude was maintained with minimal correction. The pilots reported no system anomalies in the first 30 minutes. The Maxwell moved with a fluid grace that belied the complexity underneath. Its lightweight structure and electric propulsion gave it excellent handling. As the terrain below transitioned from desert to savanna, the aircraft soared on. At the 1-hour mark, battery capacity remained at 92%. Energy draw had stabilized, confirming our models were accurate so far. The flight team began the first scheduled system scan. A visual sweep was performed from nose to tail. Heat distribution was logged. Battery temperatures were normal. Control surfaces showed no sign of strain. Ground communication was crystal clear, with real-time telemetry flowing continuously. At 2 hours, the aircraft reached the first turning point on its long elliptical route. So far, everything had gone as planned. Wind speeds were calm. There was no atmospheric turbulence to speak of. Pilots rotated control duties and initiated hydration routines. A steady rhythm began to set in. The Maxwell was eating up the miles without any sign of fatigue. Back in the control center, engineers pored over live data. Battery chemistry readings indicated a consistent discharge curve. Flight control algorithms were working flawlessly. The onboard AI-assisted systems made micro-corrections before the pilots even noticed changes. We were entering the 3rd hour. At this point, the flight officially became the longest continuous test ever conducted on the aircraft. The Maxwell was cruising at 18,000 feet. It hummed across the open skies as if it belonged there. Pilot heart rates remained steady. The cockpit remained cool and calm. Our camera drones captured stunning visuals of the aircraft slicing through the sky. From the outside, it looked almost serene. Inside, it was a test of numbers, concentration, and careful resource management. By the 4th hour, fatigue began to set in, not for the aircraft, but for the human operators. Pilots stretched and switched tasks. The Maxwell's autopilot handled basic corrections, but humans were still essential to decision-making. We didn't want to rely on automation for a test this critical. The first wave of psychological stress tests was conducted mid-flight. Simple puzzles and response tests were performed on the tablet screens inside the cockpit. Performance was slightly reduced from baseline, but within expected parameters. The aircraft itself was unfazed. At 5 hours, it had covered 1,150 kilometers. Battery charge had reached 57%. This aligned perfectly with our predictions. We had trained for this, but seeing it play out in real time was exhilarating. Even the engineers started to show signs of cautious optimism. Still, we knew the hardest part was yet to come. The halfway point was approaching. At 6 hours, the aircraft began to feel the drag of diminishing reserves. Subtle changes in handling were reported. Pilots compensated using trim adjustments. Every input mattered now. Efficiency became a minute-to-minute focus. Even adjusting cockpit lighting was discussed to conserve internal power. Flight computers began issuing advisory messages. Nothing urgent, just suggestions. We interpreted these signals and adjusted our protocols. The crew skipped the scheduled meal to maintain focus. This was no longer just a test flight, it was a performance under pressure. At hour 7, wind direction shifted slightly. The autopilot adjusted course vectors to compensate. We crossed into unfamiliar airspace where local radar support was minimal. The team had anticipated this. Satellite telemetry remained robust. Altitude held steady. The Maxwell's exterior panels began to show minor thermal variation. Sensors reported acceptable thresholds. The redundancy systems activated for additional cooling cycles. At this stage, human-machine interaction was seamless. The aircraft wasn't just flying, it was collaborating. Our team back on the ground felt every vibration through the numbers. We passed 2,000 kilometers. Battery reserve hit 34%. And still, the Maxwell pressed on. The sun began to dip low on the horizon. Golden light reflected off the aircraft's smooth fuselage. Every image captured by the chase drones told the story of quiet determination. The aircraft continued its relentless journey into the dusk. Now, 8 hours in, the test had already exceeded most historical endurance records for electric aircraft. Despite the fatigue, the mission team maintained absolute focus. The pilots ran another diagnostic sweep from the cockpit interface. Battery levels had dropped to 26%, but current draw remained consistent. A fine balance was now emerging between weight, speed, and altitude. The Maxwell's ultralight carbon composite body allowed it to glide efficiently with minimal resistance. Minor recalibrations in the autopilot system were implemented to manage descent angle without reducing thrust. Nightfall brought new challenges. Outside temperatures began to fall rapidly. Cabin heat was conserved using passive insulation rather than active systems. This strategy helped maintain internal power efficiency. Navigation lights glowed faintly against the black sky. Onboard cameras switched to infrared mode. Back on the ground, the mission control room operated under low red light to reduce eye strain. At the 9-hour mark, the pilots reported noticeable hand fatigue. Adaptive gloves with temperature control and light pressure assistance were deployed. These small interventions had been carefully designed during the planning phase. Meanwhile, telemetry still streamed flawlessly. Not a single packet of data was lost throughout the mission. The Maxwell aircraft had entered the most vulnerable phase of its journey. The final leg would push it beyond anything previously attempted. By now, it had traveled over 2,500 kilometers. The mission goal was 3,000, an almost impossible number in this category of electric aircraft. But every calculation leading up to the mission told us it was possible. Now we would see if theory matched reality. Every battery cell was being monitored individually. Thermal management systems were no longer passive. They had to intervene. Battery cooling fans kicked in at 25% reserve. This was an expected part of the flight envelope. However, their power draw was non-negligible. A tough decision was made: reduce auxiliary lighting to 0. The cockpit dimmed to darkness with only instrument glow visible. Pilots communicated using haptic taps and voice commands. Despite the low visibility, internal systems remained rock solid. We began the countdown to 10% power reserve. Data analysts projected the maximum range within a margin of just 4 kilometers. That meant we were right on the edge of success. But this was also where real stress began to reveal itself. The aircraft's handling became slightly more sensitive. Its pitch axis required manual correction for turbulence. Wind vectors at high altitude had shifted again. Every minor change now had a major consequence. Pilots engaged manual override on lateral stabilizers. The Maxwell responded like a true performer, resilient under pressure. Flight logs recorded microscopic shifts in surface temperature every 10 seconds. These readings were critical to future design improvements. At hour 10, the reserve battery dropped to 13%. We initiated pre-landing protocols. A nearby emergency strip was activated as a backup option. However, we were still within reach of the primary landing site. All data suggested we could make it. The pilots began descent at a gentle angle of 4 degrees. Air density increased, reducing forward glide slightly. Ground control gave clearance to approach. The tension in the room was electric. Everyone knew this was about to be a historic landing. At 7% battery, final flaps were deployed. Landing gear extended smoothly with no hydraulic hesitation. The runway came into view. Infrared ground markers lit the path. The aircraft touched down with elegance at exactly 9:47 p.m. local time. A feather-light bounce preceded the final contact with the tarmac. The crowd erupted into quiet cheers, mindful of the pilot's exhaustion. The Maxwell had done it. It had traveled 3,008 kilometers on a single continuous flight. All systems intact, all goals exceeded. Inside the cockpit, the pilots exhaled long-held breaths. They had pushed through every mental and physical barrier. Control tower officials confirmed landing success. The moment was historic, but we weren't done yet. Now came the most important part: analysis. The aircraft was towed to a secure hangar for immediate post-flight inspection. Thermal imaging began within minutes. Sensors were removed and connected to the central data hub. Battery banks were checked cell by cell. Only 0.8% thermal deviation was detected from pre-flight baselines. That was unheard of in test conditions. Flight logs showed less than 1% error margin from the projected endurance curve. This level of accuracy had never been achieved before in a mission of this scale. Pilots underwent post-mission evaluations. Both showed signs of cognitive fatigue but remained in stable condition. Heart rate variability data showed excellent adaptation under pressure. Psychological analysis noted improved focus during critical stages of flight. Human performance was as much a part of the story as the aircraft itself. Data compilation continued for 18 hours post-flight. Every flight segment was reviewed, every anomaly was flagged and classified. There were fewer than 5 minor deviations in total, and none of them had operational impact. This was not just a successful flight, it was proof that long-range electric aviation was real, practical, and ready. The implications stretched far beyond this single mission. Commercial aviation had taken notice. Multiple airlines had already shown interest in the Maxwell platform. But now, with this data, they had reason to invest. The test had shattered preconceptions. A clean, quiet aircraft had just performed a long-haul mission without burning a drop of fuel. This wasn't science fiction, it was fact. As the team wrapped up the mission log, a shared feeling filled the room. We had witnessed the future, and it had landed safely. The test was over, but the story had just begun. Maxwell's engineers announced the start of the next phase, international testing. Different climates, different altitudes, even ocean crossing scenarios. Each test would further cement the Maxwell as a pillar of the new aviation era. From Namibia to the world, the message was clear. Electric flight wasn't coming, it had arrived, and it could go the distance.